So wonderful. Thank you all for coming back. Apparently, we didn't scare you off. At least I didn't scare you off in yesterday's talk. So actually, Subir ended his talk with exactly the right words that fit nicely with my talk. But one thing that I was wondering about yesterday is whether it was clear to the people listening, why we were spending so much time on Lettinger's theorem. And understanding Lettinger's theorem in a non-perturbative way. But hopefully the motivations for that are now clear after listening to Subir's talk. Right? It's central to many issues that we worry about in strong correlation physics, whether it's in the cuprates or in the heavy fermion materials and so on and so forth. Okay, so in yesterday's talk, I talked about emergent symmetries and Lettinger's theorem and the tooth anomalies and metals and how all of these are connected to each other, and I illustrated that for 2D Fermi liquids and also for 1D Lettinger liquids. So today, let me just finish up on this first topic, and then I'll talk about electrical transport and clean metals. Okay. So the plan for today's lecture is to first explore the generalization of Lettinger's theorem to more general compressible quantum phases of matter, which are not necessarily Fermi liquids. Okay, so what I'll do is to provide a statement which is general to all kinds of compressible phases of matter, and that general statement in the specific context of Fermi liquids will reduce Lettinger's theorem. Right. So, and then we'll explore how this result on this generalization of Lettinger's theorem, how the result affects physical properties, and in particular, we'll focus on electrical transport. Okay, so that's the plan. And I forgot to say this yesterday, but people should feel free to interrupt me anytime during the talk with questions. You don't need to wait till the end. Okay. Yeah, so let me state the main result on these general constraints on clean compressible metals. So the statement is that the low energy theory, the IR theory of the clean compressible metal, must necessarily have an emergent continuous internal symmetry group. So what I was calling GIR in yesterday's talk, the emergent symmetry group, internal symmetry group of the IR theory, that it must necessarily be continuous. And this then implies that there's an emergent corresponding conserved quantities by Noether, which we'll call O. And furthermore, that these emergent symmetries must have a very specific tooth anomaly, which is precisely what enables you to accommodate the microscopic lattice filling that one has in the system. So the status of the statement is that we can give a physics level proof in general, but if one wants a completely mathematically rigorous proof, we're only able to prove that in one dimension. But at a physics level, we can argue for this in any dimension, one or higher. Now, if we, with some further restrictions, with some further assumptions, instead of focusing on the most general case, we make a further assumption. We can prove in a mathematically rigorous way that for any spatial dimension d bigger than 1, that this GIR must in fact be a very large symmetry group, a very large continuous symmetry group, bigger in fact than any compact Lie group. Okay, so the statement has physics level support, and various substatements have mathematical level support. So we'll just take this as something that is quite likely rigorously true, though it's not been completely established to be rigorously true. Okay.
Hi, Senthil.
Yeah.
I had a question. So yesterday you mentioned about these proofs for some gapless system, or is it true for any gapped system also?
What is true for gap systems?
This emergent existence of emergent symmetry and this 't-Hooft anomaly proof that you had?
Oh, I was specifically talking in yesterday's talk. I was talking about Fermi liquids, which are
Yeah,
obviously gapless. So they are analog in 1D, which is what we call a Ledinger liquid, which is
yeah,
also gapless, right? Yeah, so gap systems, the story is a bit different. You can certainly have, if your lattice filling is right, you can certainly have a completely trivial phase of matter where there is no emergent anomaly and so on. A simple example is a band insulator, right? Uh,
okay, yeah.
yeah. Um, uh, right. So the interesting So the focus of both my talks is really on gapless systems. Right? For compressibility, so there's a thermodynamic susceptibility that's non-zero. That is only possible in a gapless system. Is that good?
Yeah, yeah. Okay. Thanks.
Sure. Uh, so why do we call these constraints the generalized Schrödinger theorem? Right. So we're going to view this as the generalized Schrödinger theorem. And the reason is that the way Fermi liquids satisfy these constraints is by first having, for GIR, an infinite dimensional emergent symmetry. So there's the symmetry that I described yesterday with these words, the loop group in 2 dimensions. It's the symmetry group that describes smooth functions that map the circle parameterized by the Fermi surface to the circle of phase rotations of each quasi-particle at each point on the Fermi surface. Right? So the emergent internal symmetry of a Fermi liquid is an infinite dimensional continuous symmetry. It's this loop group symmetry. And we saw that the 'T-Hooft anomaly of this emergent symmetry is equivalent to the statement of Schrödinger's theorem. Right? So this structure is what in a Fermi liquid reduces to Schrödinger's theorem. And so naturally, this structure, when you're not a Fermi liquid, is what I'll call a generalized Schrödinger's theorem. Okay, it's the generalization of Schrödinger's theorem to an arbitrary compressible state of matter. Okay, so it's more abstract than the familiar statement about the volume of the Fermi surface. But if you want to make statements in complete generality, we are necessarily forced into making more abstract statements. Okay, so what can exist beyond Fermi liquids, right? From this point of view of the emergent symmetry. So there's a simple possibility that I want to emphasize, which is that the emergent internal symmetry of a class of non-Fermi liquid metals in systems where the UV symmetry group includes charge conservation and lattice translations is simply that the emergent internal symmetry is once again an infinite dimensional emergent continuous symmetry. Perhaps it's exactly the same as a Fermi liquid, or perhaps it's a small variant of what's there in the Fermi liquid, right? So it's this so this is a class of potential states of matter which are beyond Fermi liquids, which share with the Fermi liquid the property that the low energy theory has an infinite dimensional emergent continuous symmetry. So we've been calling these ersatz Fermi liquids. Ersatz means replacement for a Fermi liquid. Now, over the years, there have been many models that have been constructed in the condensed matter literature for non-Fermi liquid metals. And almost all these examples that exist in the literature fall in this category of systems with an emergent infinite dimensional continuous symmetry, which is more or less the same as the emergent symmetries of a Fermi liquid, right? So there's a huge class of examples that we have with this structure, what we may call these ersatz Fermi liquids. Now, you can wonder whether there's a more exotic structure of emergent symmetries that are possible. And the answer seems to be yes. There certainly are examples that we've constructed where the structure of emergent symmetries is somewhat more is different from what's from that of an infinite dimensional symmetry group. They involve the kinds of things that high energy physicists have dubbed higher form symmetries in the last few years. So I'm not going to say much more about that, mainly because this class of non-Fermi liquid metals with infinite dimensional emergent continuous symmetry is already extremely rich, but nevertheless is very poorly understood. So we'll just think about think about this class. But the general statement that I made in the previous slide, that there's an emergent continuous internal symmetry, whether it's infinite dimensional or not, seems to be true in all the examples that we have so far. Right? So there's no counterexample that's known to the statement that there's a continuous emergent internal symmetry group. And that's all that I'm really going to need for the rest of the talk. Okay. So it's an interesting question whether this emergent continuous symmetry group is infinite dimensional or whether it involves these more complex structures like higher form symmetries and so on and so forth. All right. Okay. So even if the IR symmetry group turns out to be exactly the same as in the Fermi liquid, right? And the anomaly of this IR symmetry group, both the symmetry group and the anomaly, turns out to be exactly the same as in the Fermi liquid. We cannot conclude that the resulting state is necessarily a Fermi liquid. The only thing we know is that these kinematic properties that are determined purely by this structure of the emergent symmetry and the anomaly, will be the same. The dynamical properties can nevertheless be very different and make the state a non-Fermi liquid. Okay, but at any rate, this continuous emergent symmetry means that there are emergent conserved quantities, and if it's an infinite dimensional continuous symmetry, then there are an infinite number of emergent continuous conserved quantities. And the presence of these conserved quantities has very strong implications for all kinds of dynamical properties of the resulting state. As you can imagine, every time you have a conservation law, that tells you a lot about, gives you a lot of constraints in the dynamics of the system, right? And in particular, there are very strong implications for transport in a system with emergent continuous symmetries, and that's what I want to explore in the remainder of this talk. Okay. So I want to talk about electrical transport and clean metals. So everything that I'm talking about in these lectures is about clean metals, no impurities. So I want to talk about general constraints on electrical transport and explain how there may be a route to non-Fermi liquid transport in a clean metal that satisfies these general constraints. Okay, so let me start with a very simple statement about transport and conservation laws. So electrical resistivity in a metal requires the mechanism for an electrical current that you set up to decay. Okay.
Hi,
so if you prepare, yeah.
Can I ask you a question? So trying to understand your statement. So yesterday you constructed the loop group for defining this n of theta. Now, are you saying that similar n of theta type of variables can be defined in context of these extended sort of Fermi liquids to define a low energy symmetric group which is infinite dimensional, and you're talking about the constraints that are placed by that group?
Absolutely, yeah. Everything you said.
Even though n of theta may not be well defined objects?
No, n of theta are well defined, but there need not be any quasi-particles. Right? So in a Fermi liquid, n of theta sort of describe everything that's there at low energies.
Okay, then can I just ask a follow-up question regarding the statement that you just made? You said that n of theta, defining n of theta does not necessarily mean there are quasi-particles. Can you? Okay. So how about these spin-on Fermi surface states with transverse gauge field fluctuations where different patches couple? Even there, n of theta is well defined.
Yeah. So there is some notion of So the point is whether in that example, for instance, the number of fermions in each patch of the Fermi surface, whether it's conserved or not, right? and it is conserved in the low energy theories that we have been working with, right?
Okay, I see. Thanks.
But the quasi-particle is not well defined.
Yeah, okay. Thanks.
All right. So let's just think very generally about transport. So as I said, electrical resistivity requires a mechanism for electric current to decay. Right? If you prepare the system in some current carrying state and let it go, that current has to decay to zero for the system to have any electrical resistivity. So you could imagine, for instance, in a metal or in any system, disturbing it by turning on a pulse of electric field that, over some short time interval, turning on an electric field and letting it die to zero later, right? Now, the system will respond with an electrical current, and you could ask what happens at late times to this electrical current, right? Does it go to a zero value or does it go to a non-zero value? Okay. Now, if in this process of turning on this electrical pulse, you excite the system into, you will excite the system into some state. And if in that process, the electrical current that you initially set up mixes with some conserved quantity, and as it evolves in time, if it sets off a non-zero value of some conserved quantity, then at long times, that conserved quantity will not decay to zero precisely because it's conserved. And the presence of non-zero value of the conserved quantity will in turn lead to a non-zero value of the current, right? So generically, if the electrical current can mix with a conserved quantity, then you might expect that the shape of this blue curve, the current in response to this electric pulse, will be such that it asymptotes to a non-zero value at infinity, okay? Now, the conductivity is the current induced in response to an electric field. Here I've plotted in the time domain. If you take a Fourier transform of this picture, then the statement that I want to make, if that is J infinity is non-zero, then the real part of sigma of omega has a delta function piece, right? And I urge the students who are listening to this talk to prove the statement. This is a simple exercise in Fourier transformation, which I'm not going to explain, but I urge you to think and convince yourself that the statement is true. Okay, so in other words, if the current doesn't decay, which will happen if the current can mix with a conserved quantity generically, so then the DC conductivity is infinity. This delta function is infinity at zero frequency, which means that there is no electrical resistivity. Okay. And this fact is in fact familiar in, say, a continuum Fermi liquid with which obviously conserves momentum. So let me illustrate the standard argument for this familiar fact in the next slide. So if you have a theory with a conserved momentum density, P, so you can think about a continuum Fermi fluid, perhaps with interactions. So with the conserved momentum density, we can consider a modified Hamiltonian density, which is standard Hamiltonian minus V dot P, where V is, we can think of as the overall velocity of this fluid. Now the electrical current density that's induced in response to this velocity will be given by some susceptibility chi Jp times the velocity. And usually we just call this chi Jp the electrical charge of the system, right? So the current is charge times velocity, which is the charge density times velocity, which is a familiar statement. Now the average momentum that's induced by this V dot P term is given by a self-susceptibility, chi Pp times the velocity. And this is what we usually call the mass of the system, right? Momentum is mass times velocity. Now, in a uniform electric field, we know that there's a Newton's law, dP dt is Q times E. And combining this, so given that P is determined by V and J is determined by V, this then gives us an equation, dJ dt is Q squared over M times E, which we can also write as chi Jp squared over chi Pp times E. And Fourier transforming this gives us a relationship between current and electric field, And Fourier transforming this, we indeed get this delta function piece for the real part of the conductivity. Right? So if you Fourier transform this, you'll get the complex conductivity, and then taking the real part, you'll get this delta function piece. Okay, so this is hopefully a familiar statement in about an ordinary system with a conserved momentum density, but the statement is more general. Okay, so motivated by this, let's pose a few very elementary questions about electrical resistivity in a metal. So if you do not have a continuum system, but rather you have a system in a lattice, so you can ask whether a clean metal on a lattice can at all have an electrical resistivity. And you might imagine that it's possible because, after all, you don't have a continuous translation, so you don't have momentum conservation. So it's more interesting, in fact, to consider the opposite question, whether a clean metal can ever support a dissipationless current, a current that just lives forever, right? Which is equivalent to a zero resistivity. And the answer to the statement may be a bit is a bit complicated, because there is a famous theorem that was stated by Bloch. So that most people have heard of Bloch's basic theorem on motion in periodic structures and how crystal momentum eigenstates are well defined, blah blah blah. The first thing you learn in solid state physics. But there's another theorem that Bloch stated, which was published by Bohm. So it's somehow not called Bohm's theorem, because I think it was really articulated by Bloch, that for a system in thermal equilibrium, the electrical current is zero, right? So this then raises the question of how you can ever support a dissipationless current. Okay, so let me give an answer to this question by first reviewing a modern proof of Bloch's theorem. Okay, which really only appeared in the last couple of years. Okay, so it's an interesting and very simple proof. So it's worth learning this proof for its own sake. So let's think about the system of charged particles with a conserved global U1 in the grand canonical ensemble, right? So there is some density matrix 1 over z times e to the minus beta h minus mu q, and this satisfies an inequality which tells you that the thermal equilibrium state has the lowest free energy, right? Which is a familiar statement in thermodynamics. So, but it can be recast as the statement that the expectation value of V dagger kV in this thermal ensemble is always bigger than or equal to the expectation value of K itself for any unitary operator V. Okay, so let's apply this general statement to a slow rotation, to a slow U1 rotation, right? So we use the generator, the charge density of global U1 rotations. And rather than doing a global U1 rotation, we do a slowly varying rotation with some function lambda of x. The lambda of x varies slowly compared to all length scales in the system. Now, and we can ask what the left-hand side of this inequality becomes when we choose such a V. And it shouldn't surprise you that the expectation value of V dagger kV, so essentially you're doing a gauge-like rotation in the system. So naturally, the system responds by average V dagger kV being the deviation from average of K is determined by the integral of the current times the gradient of lambda, right? So the answer can only depend on the gradient of lambda, because if lambda is a constant, then V is the symmetry operator, and then V dagger kV is just equal to K. So, but if lambda is slowly varying, the deviation from K is going to depend on the gradients of lambda, and by definition, the coefficient is the current, right? So combining this with this inequality, and I'm skipping some steps, but you can read about it in these papers. This paper actually makes it completely rigorous. One can show that this inequality implies that the average current is zero, which is Bloch's theorem. Okay, So it's a very nice way of thinking about Bloch's theorem. But now let me discuss a loophole to Bloch's theorem armed with this modern understanding of the theorem. Okay. So suppose that in addition to the total charge Q, there is another commuting conserved quantity O. Okay. So what I mean by that is that O commutes with the Hamiltonian, so it's a conserved quantity. And furthermore, O commutes with Q itself, so that we have the complete set of conserved quantities that involve the Hamiltonian include both Q and O. Okay. So then thermal equilibrium is described not by the standard grand canonical ensemble, but it's described by a generalization, that by what's known as the generalized Gibbs ensemble, where we also include a list of thermodynamic quantities apart from the energy and Q. We also have to include O and the corresponding conjugate thermodynamic variable, which I'll call H. Now let's rerun the proof of Bloch's theorem. We'll use the same V as in the previous slide, make a slow global U1 rotation, right? Now, when we run that proof of Bloch's theorem, what we need is the commutator of the charge density with this operator O, right? Because, what's involved is B dagger KV, and B has this operator N of X. So when you expand this out in powers of lambda, you're necessarily going to get the commutator. Okay. Now the commutator of Q with O vanishes, which means that this commutator, it must be such that its integral over all space vanishes, right? But this commutator itself need not vanish. It's only its integral that needs to vanish. Okay. Now suppose this commutator is equal to minus I times the gradient of some function sigma. This will guarantee that its integral vanishes, right? But it's allowed to be non-zero in the form of a gradient. Then rerunning this proof, one can show that the average current is in fact not zero, but instead is given by H times the average value of sigma integrated over the entire sample. So this then gives you an equilibrium current so long as average sigma is non-zero. So long as this commutator is non-zero, you get an equilibrium current. Okay, so it's a very simple statement. So you can ask in this equation, when can this commutator at all be non-zero? When can this function be non-zero? And here there's a very nice condition on when this can be non-zero. Suppose we regularize the system on a lattice, right? Which after all in condensed matter physics is what we have. So then the N of X, the total charge, is the sum of terms like Ni. Is the sum of the charges at each lattice site. Now the symmetry generator O is the sum of operators OI defined on each individual lattice site. Then the only way we can satisfy the relationship that the total charge and total O commute with each other is to necessarily have that each OI commute with the charge at that site I. Then we necessarily have this feature that the commutator of N of X with O is zero, so that sigma itself is zero, right? So in the usual case where both the total charge and the symmetry generator O can be written as the sum of operators defined on individual sites, this commutator is zero, and there's no loophole to Bloch's theorem. So this condition can be expressed by saying that O must be a symmetry operator that cannot be localized as acting on individual sites of the system. It's what's sometimes in the condensed matter literature called a non-on-site symmetry. So there's two examples of such non-on-site symmetries that one could imagine. First is that it's a space-time symmetry. It's a spatial symmetry like continuous translation symmetry, if you had that in the system. For instance, if O is the momentum, then it's a simple example to work out the commutator of the charge density with the momentum in a theory with in any theory. And this sigma then can be shown to just be the density itself. And we reproduce the familiar result that the current is charge density times the velocity. Right? Now, we are interested in lattice systems with no continuous translation symmetry. So we're interested in systems which have an internal symmetry. So then how can this commutator ever be non-zero? And the only way in which this commutator can be non-zero is if we have a problem with regularizing the system on the lattice while preserving the symmetries, right? Now, that's precisely one meaning of the word anomaly, right? So anomaly in a symmetry refers to a situation in which you can't have a good regularization of the lattice while preserving the symmetry as non-side symmetry. So the symmetry generated by O as a mixed anomaly with the global U1, right? And again, the simplest example of this situation is the chiral anomaly of the massless Dirac fermion in 1+1D. So then this commutator is allowed to be non-zero, and in fact, this function sigma is just related to a quantized anomaly coefficient with it's m over 2 pi, where m is an integer, which is a quantized number that characterizes the anomaly. So if you do not have continuous spatial symmetries, the only way in which you can get this loophole to Bloch's theorem is by having an emergent symmetry, an emergent commuting symmetry that has an anomaly. Okay. All right. Now, there's another way of thinking about this dissipationless current. So if you have an equilibrium state that's described by this generalized Gibbs ensemble, now you might we just saw that the current may be non-zero if there's a mixed anomaly between these two symmetries. Now, on the other hand, just from thermodynamics, we can also write the average value of the current as H times a cross susceptibility between the current and this observable O, right? That's just the definition of the cross susceptibility. So what we see is that if there is a mixed anomaly, so that this coefficient is non-zero, this response is non-zero, then this cross susceptibility between the chi j o between the current and this emergent conserved quantity, this cross susceptibility is determined entirely by the mixed anomaly, right? So there's a very, very general relationship between this cross susceptibility and the mixed anomaly between these two symmetries. Okay. Now let's recall. Let me connect this general discussion with the generalized Schrödinger constraint that I started this talk with. Okay. So the generalized Schrödinger constraint was that.
Can I ask a question here?
Sure.
Yeah, just curious. I mean, if I just take a lattice in one dimension and put periodic boundary condition, of course, it's not an open system. But then if I stick in a flux, I will get a spontaneous current. And which category will it fit in this discussion? I mean, in the ground state, I'll get a current because of the flux. And I'm not able to fit into any of this. It's just like you break time reversal, and so you get a persistent current in the ground state, which will not decay in general.
Sorry?
Which will not decay in general, I mean, unless I put in something else.
Right. So the persistent current in a 1D metal, and at least in a clean 1D metal, is so really what you have is you have a non-zero value of this axial charge, right? N right minus N left is non-zero.
Yes.
And it's the conservation of that protects the thing from decaying. So it's precisely one of these, you can think about it in precisely these terms.
I see. So what would be the statement there? What will be the conserved quantity which will...
it's precisely N right minus N left.
Oh, I see. Perfect. Okay.
Right, okay. Which has a mixed anomaly with N right plus N left.
Right. Okay, fine. Thank you.
Sure. So the statement was that the low energy theory must have an emergent continuous symmetry group, therefore emergent conserved quantities, and furthermore that these symmetries must have an anomaly. In fact, the anomaly is of precisely the form that it's precisely this mixed anomaly between O and the global U1 charge that guarantees that this cross susceptibility is non-zero. So this emergent conservation law associated with this symmetry is violated by external electromagnetic fields. So dO dt is m over 2 pi e. Again, think about the 1D metal for concreteness. So I'm writing all these equations as though I don't have spatial indices, but they can be generalized to higher dimensions, which we see is simply chi j o times E, because this anomaly coefficient is precisely this cross susceptibility, right? So the anomaly has guaranteed for us that the anomaly of this emergent symmetry that we argued must be present on general grounds has guaranteed for us that the electrical current has a non-zero overlap with this emergent symmetry, with this emergent conserved quantity. Okay. This then leads to a dissipationless current on general grounds, right? So I established that the statement is that if you have a conserved quantity that overlaps with the current, then generically you might expect to have a dissipationless current. But on general grounds, we argued, or rather I stated, that a clean compressible metal on a lattice will have a continuous symmetry group with precisely the right kind of anomaly. Okay, so let's flesh this argument out a bit more. So let's go back to thinking about what happens if we start our system off and turn on an electrical pulse that dies off, a pulse that's shaped like this red curve here. So let's even think about a delta function pulse at time t equals 0. We have the anomaly equation, dO dt is chi Jo times E. So this implies that if I integrate this equation from minus infinity to plus infinity, given this shape of the electric field, this implies that the quantity O changes by chi Jo times epsilon. I guess I'm missing a subscript 0 here, but sorry, that's a typo. So the change in delta O is simply the integral of this equation, and with the delta function pulse, it just changes by chi Jo times epsilon, right? Now, correspondingly, the conjugate thermodynamic variable, so this disturbance will move the system from its initial equilibrium state to some other new equilibrium state at late times. And this new equilibrium state will have a shifted value of the conjugate thermodynamic variable that's given by, the change in delta O divided by the self-susceptibility of O with itself, right? Delta O divided by chi OO, which combining these two equations, I write as chi Jo divided by chi OO times this epsilon, okay? So now we can ask about the current that's induced in the system at late times. We can calculate J infinity. And this current, so we saw in the previous slide that the current is, by definition, is chi Jo times H. So this then gives us that assuming that the current in the initial equilibrium state is 0, this gives us the late time current as chi Jo times delta H, which combining all these equations is chi Jo squared over chi OO times epsilon, right? So this is a more general discussion of the same kind of equation that characterized the translation invariant Fermi liquid, where again, we saw that there was a dissipationless current that was proportional to chi Jp squared over chi Pp. We just replaced that with a more general discussion where this O, the momentum is now replaced by any internal symmetry O that is a mixed anomaly with the global U1. Okay. So generically, what we seem to get is a dissipationless current and hence infinite DC conductivity. Okay. So on fairly general grounds, we seem to have reached this conclusion that a compressible metal will have an infinite DC conductivity. Okay. Now let's ask what happens in a conventional metal, like clean Fermi liquid, perhaps on a lattice. Now the low temperature conductivity in a clean Fermi liquid arises entirely through mechanisms that dissipate the momentum, right? So if you have a lattice, Fermi liquid defined on the lattice, then there's no true momentum conservation. Momentum is only conserved modulo the reciprocal lattice vector of the lattice. But operators in an ordinary Fermi liquid, in the IR theory, operators that break the that involve this process where momentum is transferred to the lattice of irrelevant operators. They are what's known as Umklapp operators in the condensed matter literature. So it's if you don't have impurities, conductivity in a clean Fermi liquid, in a clean lattice Fermi liquid, necessarily comes from irrelevant operators that are not there, the fixed point theory, but they will be there at some non-zero temperature, but weakly, which are able to transfer momentum to the lattice. Okay. Now, of course, in real Fermi liquids, momentum is also relaxed efficiently by scattering of random impurities. Okay. Now, in more general examples, the current will overlap with all IR conserved operators which which have the same symmetry under GUV. And this, so long as this overlap is non-zero, which I've argued will be true because of the anomaly, these will in general lead to a delta function contribution to the real part of the conductivity, so infinite DC conductivity. So let me now briefly mention a problem with this general conclusion, a potential problem with this general conclusion, with things that we seem to be learning over the decades from experiments on several strange metals. For instance, in the cuprate strange metals, there's been a lot of discussion in the experimental literature showing that suggesting that the measured conductivity, sigma of omega and t, behaves in the following form. It's 1 over the temperature, some prefactor, times a function of omega over t, where this function is such that it has a finite non-zero value when its argument goes to 0. So in other words, the measured conductivity satisfies some scaling form, which is such that there's no intrinsic energy scale in the low energy theory, and the only energy scale is set by the temperature. Okay. This suggests that the low energy physics of the strange metal, the IR fixed point, is controlled by a scale invariant theory plus various irrelevant perturbations. And furthermore, that the strange metal transport, because it satisfies a scaling form with no intrinsic and with no energy scale other than the temperature itself, it suggests that the strange metal transport is a property of the scale invariant theory itself and is not determined by any irrelevant perturbations. Okay, so if we accept this conclusion, this reading of the what is suggested by the experiments, then it seems like we have a problem, because what the experiments seem to be telling us is that the scale invariant theory has no delta function conductivity, right? So that kind of conductivity would be inconsistent with what's actually measured in the experiments. It's 1 over t times, there's a finite DC conductivity that's measured that is part of a scaling form with the frequency dependent conductivity with no energy scale other than the temperature, right? And that's inconsistent with an infinite DC conductivity. Okay. So this then tells us that the measured resistivity. So there's a famous fact in these experiments that I glossed over in the previous slide, and that's the prefactor. The prefactor goes like 1 over temperature, which means that the DC conductivity goes like 1 over temperature. That means the DC resistivity is linear in temperature. And this is a very famous phenomenon. It's perhaps the most famous phenomenon of experiments on these strange metals. And that famous linear temperature resistivity is, we might then be led to conclude that it's not determined by the slow relaxation of nearly conserved quantities, but is instead an intrinsic property of the scale invariant low energy theory. And I should emphasize the basic assumption that I made right at the beginning of the talk, saying that we can ignore, the assumption was that we can ignore random impurities. I didn't try very hard to justify this assumption in these lectures. I just said, let's make this assumption and see where we go, right? So we'll continue to make this assumption and see where we go. And maybe at some later stage, we have to revise this assumption, right? But if we continue to make this assumption, then this source of relaxation of conserved quantities is not available to us. And so then we have to deal with a clean system, which is subject to all these generalized Ledinger constraints and anomalies and so on. And those constraints are powerful enough that they seem to force us, more or less, to have a dissipationless current and infinite DC conductivity, while the experiments seem to force us to not have such a dissipationless current, right? So that's the issue. So without relaxing this assumption, is there a way out? Okay, so let me re-emphasize, because I think this is very important. So to repeat myself, so there's two different conclusions that we've reached. One is from reading the experimental data that the strain metal transport is an intrinsic property of the IR fixed point theory. And the second is that from theory, that the IR fixed point theory has emergent conserved quantities whose overlap with the current is guaranteed by the mixed anomaly, right? And this in turn implies, seems to imply naively, a delta function conductivity of the fixed point theory. So these two things are in tension with each other. So there is one possible resolution of this tension without relaxing the assumption of no disorder that we made. And that the solution is that the susceptibility of all the conserved quantities that overlap with the electrical current, that they diverge, right? So the expression for the delta function piece is this anomaly coefficient, which is necessarily non-zero, divided by the self-susceptibility chi OO, right? Or equivalently, if I go back a few slides, the strength, the value of this late time current is chi JO squared over chi OO times the height of this delta function, right? Chi JO is non-zero, that's guaranteed by the anomaly. So the only way I can have a zero late time current and hence no dissipationless current is to have chi OO be a diverging quantity. Okay. So if chi OO diverges, then we kill the delta function and then we suppress this contribution to the conductivity, and other what's known as this incoherent contribution can then dominate the response. So what are these observables that we think need to have a diverging susceptibility to resolve this tension? So as I said, the current will overlap with all IR conserved operators which have the same symmetry under GUV, and their susceptibility must diverge at the strain metal fixed point. So these operators, since they have the same symmetry as the electrical current, they must be odd under time reversal and inversion. They must have zero crystal momentum, and they must transform as a vector under lattice rotations. Right? Under the lattice, discrete point group symmetry, which for the square lattice is just fourfold rotations, they must transform as a vector under these fourfold rotations. Right? So these are the same symmetries as an order parameter that has been discussed extensively in the cuprate literature. It's known as the Verma loop current order. It corresponds to an order that's associated with circulating electrical currents that live inside each plaquette of the two-dimensional square lattice, but this pattern of currents doesn't break translational symmetry. So this pattern of currents, so what's here I've shown a single copper oxygen plaquette. Subi showed the electronic structure of these materials. So it's copper oxygen planes. There's copper sites, which are the important sites that form the vertices of a two-dimensional square lattice. And an idea that has been advocated by Chandra Verma for 25 years is that for some reason that there are circulating currents within this unit cell. An example of such a current pattern is shown here. So there are currents that go around like that. That's the proposal. And this current pattern has exactly the same symmetries as this operator whose susceptibility we need to diverge to suppress this delta function contribution. So Verma advocated this for various reasons that I'm not sure I completely understand. But motivated by his advocacy, there have been a large number of experiments done in the last 15 years that look for such loop current order in these cuprate materials. Most of them focused on the pseudo gap regime that Subir mentioned. And by now, there's many reports of static loop current order in the pseudo gap regime. And there's also many controversies, right? So the experimental situation is that there's maybe 5 or 6 totally different kinds of experiments that suggest that this kind of order is actually there in these materials. But each one of those experiments is disputed by other claims in the literature, which which one could also give some credibility to. So at the end of the day,
excuse me, Senthil?
Yeah.
Yeah, you have about 10 minutes left, including your 5 minutes for questions. So you can allot it as you wish.
Yeah, I'm
Okay.
almost done. So I'm about,
Yeah.
I'll be done in a couple of minutes, actually.
No problem. I just heads up.
Yeah. Oh, great. Thanks. So the dust has hardly settled on whether this sort of loop current orders exists in static form in the pseudo gap regime or not. And even if it exists, it's hardly clear, at least to me, what aspect of the pseudo gap phenomenon one actually understands. Now, there are other ideas for why loop current order might exist. In the literature, I won't really describe these. Both these proposals, both these ideas suggest that it's really not a primary order parameter, but rather it emerges as a secondary order parameter due to fluctuations of some more basic order parameter, as a composite order parameter that emerges as when you have fluctuations of some more basic order parameter. But in any case, I think it's fair to say that theoretically, it's not very clear microscopically why you need to have this kind of order. At least it's not clear to me why you need to have this kind of order in the cuprates. And experimentally, it's not clear that this order is not there. It's also not clear that this order is actually there. So the situation is a bit confused, both experimentally and theoretically. Now, what we've ended up with, the place we've ended up with, coming from these completely general and totally different considerations from anything else in the literature, is that we have a completely different rationale, a completely different role for critical fluctuations of this order in the strange metal regime of the cuprates, right? And we reach this, by making some general assumptions and thinking about the constraints that follow, but without ever having to write down an actual Hamiltonian for the system, right? There's not a statement that we reach at by trying to solve the Hubbard model or anything like that, but rather I've walked you through the logic, and it's just, very general model independent considerations. So some of the assumptions we've been making at various stages, we need to scrutinize them in great detail. For instance, is disorder not really important, or it plays a role in some hidden way? And some of the more theoretical assumptions that we've been making will also need to be scrutinized. Since I'm not completely out of time, let me mention one other thing of this story for the strange metals, another a different kind of experimental test. An experimental test of the statement that the strange metal transport is not associated with slow relaxation of conserved quantities. This is completely different from a Fermi liquid, where transport is entirely due to slow relaxation of conserved quantities. So a consequence of this is that if you have a strange metal quantum critical point that is proximate to a standard Landau Fermi liquid, the Fermi liquid famously has a T-squared resistivity that comes from the slow relaxation of conserved quantities. So the statement that we are led to is that that t-squared resistivity will not be part of a scaling function with whatever resistivity characterizes the same metal, right? So if you measure the resistivity of the same metal and you measure the resistivity as a function of the deviation from this critical point and try to collapse all the data to a scaling form, you might have hoped that the same scaling form captures both the strained metal transport and the Fermi liquid transport. But given the different mechanisms involved for transport in the strained metal and the Fermi liquid, we would think that the same scaling function will not capture both of these. And this is something that could be tested experimentally in some systems. All right, so let me just summarize my thoughts. So what we've seen is that charge conservation and the assumption that the microscopic system is clean, that it has lattice translation symmetries, and that it is compressible, that it has a tunable filling, these assumptions lead to strong constraints on the IR theory, and the further assumption that these symmetries are not broken at the IR fixed point. These lead to strong constraints on the IR theory that must be satisfied by any putative non-Fermi liquid. It's certainly satisfied by Fermi liquids in the way of Lodinger's theorem, but it must also be satisfied by putative non-Fermi liquids. And we see that anomalies and other topological structures play a crucial role, and they enable model-independent statements. And this is true of in quantum field theory as well. The power of thinking about anomalies and anomaly matching and things of that sort is that you're led to very general constraints which are model-independent, right? And the application to the specific condensed matter systems that we are interested in, for the strained metal itself, so we reach interesting statements about transport in the strained metal, right? That it's not related to the slow relaxation of nearly conserved quantities. And second, that if you attempt to explain the strained metal phenomenology within the framework of a clean model with no disorder at all, then it's consistent with the general constraints, only its susceptibility of certain observables to the same symmetry as this loop current order parameter diverges. Okay. So a big question in the strategy for progress that I've described in these talks is how far can we milk this approach of trying to make general statements without committing to a detailed dynamical model. Clearly, we can only get some distance, right? Ultimately, we have to talk about detailed models which incorporate these constraints if we have any, to get a full understanding. But is there further that we can go? And perhaps we can, but perhaps we can't. So let me leave it at that stage and stop. And thanks for your attention.
Thank you very much. Are there questions immediately?
Yeah.
Hi. You talked about the cubics, but for the other systems like the heavy fermions where we see strange metal behavior, are there similar loop current-like order parameters that naturally explain the strange metal behavior?
No, so I'm not aware of experiments that look for this kind of fluctuating order at the heavy fermion quantum critical points. Besides, I should caution that I'm not, the statement I'm making is not that loop current fluctuations explain the strange metal.
Sure.
Right? I don't think the theory that I've discussed enables me to make that statement. What the loop current fluctuations enable us to do is to get rid of this dissipationless current. And then there's the entire question that I've not touched on at all, what actually describes the incoherent conductivity, right? And that's the next problem. I mean, if we can get rid of the coherent conductivity, the burning question becomes, what's the incoherent conductivity? And that's what needs to be solved. Right? But we didn't solve that at all. We haven't even attempted to solve it.
Right. I was just trying to understand if I mean, your proposal seems to be tied with the fact that there is a order parameter with the right symmetry, which becomes critical to get rid of the coherent part.
Right.
So are there theoretical
And strictly
proposals for
speaking,
even other
sorry,
systems?
Shubha, let me interrupt. Strictly speaking, I mean, nothing in what I said even demands that one side of the phase transition needs to have static order with these symmetries.
Absolutely.
Right? We know of many examples of quantum critical points where there's diverging susceptibilities of some observable, but that observable is not ordered in either phase. So, yeah.
Okay. Okay. Yeah. Thanks.
Are there other questions that anyone has?
Can I ask a question? Yeah. So,
Go ahead.
So this is regarding the formulation essentially. What you said, these are the dissipationless currents which you came to, and they don't decay. So can I think of them in terms of like I will go back to the ring problem. There, I think sticking in the flux is like generating a spectral flow, and that resulting to this persistent current. So from that point of view, of course, one can think that when you stick in the flux, there's a rate of change of flux, and there's an electric field generated which is circulating the current, driving the current in some sense. So it's for a closed system. So, but the spectral flow is somewhere in the game. Can one formulate this problem from this perspective, more from a pumping kind of perspective for these dissipationless currents, or it's a curiosity? I'm just curious if one can.
You may be able to. I don't know. Yeah, it certainly may be possible. It's not a direction that I've tried to think about myself, but feel free to think freely about it.
Okay, thank you. Thank you. Okay.